Let's just jump right in, shall we? Today, we're setting out on a truly fascinating journey to completely reframe how we perceive, teach, and honestly just learn mathematics. For anyone who has ever felt totally disconnected from numbers, or if you're an educator trying to reach struggling students, looking at math through this new lens, it changes absolutely everything. Think about this quote for a second from Dr. Robert Kaplan. And they are slaves to math for life. It's intense, right? But it perfectly establishes the high stakes of poor math education. When we rely strictly on rote memorization and endless uncontextualized drills, we literally leave countless learners feeling trapped. They feel anxious, basically chained to a subject they don't truly understand. So, what does this all mean? Well, what if we've been teaching math completely wrong all this time? It's a massive paradigm shift. We've got to stop viewing math as just this rigid set of numbers and formulas. Instead, we need to see it for what it truly is, a dynamic, living language. It has its own grammar, its own syntax, and a really rich vocabulary. When we unlock the language of math, we unlock math itself. Okay, let's dive right into this. Here's our roadmap for the explainer. 1. Math is a language. 2. Escaping mechanistic teaching. 3. Comprehensible input and processing. 4. Output and constant feedback. And 5. The unified teaching model. All right, section 1. Math is a language. Now, research reveals something totally astounding. Native English speakers face the exact same hurdles with academic math as English as a second language learners face when learning English. Why? Because academic math basically acts as a complex third language. When you break down the elements of mathematical discourse, it's pretty eye-opening. Math actually contains morphology, semantics, and syntax right alongside conceptual understanding and procedural fluency. Just like learning French or Spanish, learning math means you have to grasp how specialist syntax and sentences are constructed to actually create meaning. To actually learn this language, the researcher Moshkovich lays out 3 distinct perspectives. First, acquiring vocabulary, which is the mathematical register. Second, constructing meanings. This basically means shifting a word from its everyday casual use to its precise mathematical use. And third, participating in discourse. You aren't just memorizing words, you're using social and linguistic resources to actively participate in mathematical conversations. Moving right along to section 2, escaping mechanistic teaching. So historically, we relied heavily on the 1960s mechanistic approach. We're talking passive learning, rote drills, and closed questions. To put that into perspective, it's the exact equivalent of trying to learn conversational Spanish by silently reading a dictionary. It simply doesn't work. Contrast that with the modern realistic mathematics education, or RME approach. This focuses on active problematization, guided reinvention, and rich interaction. This is how you actually gain fluency, by doing, by speaking, and by solving real-world problems. Let's see how this builds in section 3, comprehensible input and processing. Okay, so here are the 4 pillars of language acquisition that researchers have found map perfectly onto mathematics. 1. Comprehensible input. 2. Language processing and interaction. 3. Output. And 4. Feedback. Let's break down exactly how steps 1 and 2 actually work in a math setting. Step 1 relies on this really brilliant concept, Krashen's formula of I plus 1. Basically, for a learner to acquire language, the input they receive must be just a bit beyond their current level of competence. It should be challenging, sure, but still meaningful and comprehensible. In math, this links perfectly to the reality principle, using real-life problems that anchor the unknown math concept to something the student already understands. But just hearing input isn't enough. It must become intake during step 2, which is processing and interaction. Learners and teachers must negotiate meaning. A great example of a clarification request from our source is a teacher using a rising intonation on a wrong word. Say a student says denominator when they actually meant numerator. The teacher simply says, denominator? With a rising pitch. This prompts the student to internally process, reflect, and self-correct on the fly. Another absolutely incredible tool for processing is the use of recasts. A recast is when an educator rephrases a learner's incorrect statement by modeling the correct mathematical form, but without explicitly saying, hey, you're wrong. This is a brilliant way to provide the correct academic syntax without discouraging the student's linguistic risk-taking. It just keeps the conversation flowing naturally. Let's jump into section 4, output and constant feedback. So the crucial point here is that output forces learners to test their hypotheses through various communication strategies. A fascinating one is the memory strategy, which involves creating mental linkages. For example, a student might use the physical, rectangular shape of their own desk as a visual memory strategy to remember geometry formulas for calculating area. Output isn't just writing down an answer, it's utilizing strategies to actually communicate a concept. And of course, output requires feedback to be effective. This brings in Vygotsky's zone of proximal development, or ZPD. This theory highlights the deeply social, interactive nature of math. True feedback requires group work and guidance from a more knowledgeable other, like a teacher or even a peer. Learning math isn't a solitary act, guys. It's a collaborative, social endeavor. We can actually apply a highly practical matrix of scaffolding strategies to that feedback. Think about how a teacher can respond to a student's output. If a student says the graph goes higher, the teacher reformulates it into academic language. Yes, the graph does rise steeply. Or they might ask for precision. What do you mean by it? Or even use gestures to signify a horizontal axis. These tiny, constant feedback loops slowly but surely build mathematical fluency. And finally, Section 5, the Unified Teaching Model. This cyclical model brilliantly brings all of these theories and strategies together into one cohesive system. You start right at the beginning with comprehensible input, guided by questioning techniques. The process then pulls you into language processing and interaction, where meaning is negotiated. That flows directly into output, where students verbalize their mathematical solutions, which then triggers feedback, scaffolding the learner right back into more advanced input. It's like a constant dynamic engine of language acquisition wrapped entirely in mathematical proficiency. So here's my question for you. If math is a language, are you ready to finally become fluent? By viewing math through the lens of comprehensible input, processing, output, and feedback, we strip away all the fear and the boring rote memorization. What we're left with is a beautiful, logical discourse. Take this framework, apply it to your own learning or teaching, and start speaking the language of mathematics. Thanks so much for joining me on this explainer, and keep exploring.